Here we're going to look at radiometric dating, and this is going to be determining the absolute age of a rock, and we can find this activity in our binder. That we use the principle of radiometric dating to provide a numerical age to date the rocks and or minerals that contain the radioactive isotopes, such as uranium-238 and potassium-40. These spontaneously break down or decay to form stable isotopes. For example, radioactive potassium-40, the parent isotope, decays into a stable argon-40, and this is the daughter isotope. So the decay rate is often described in terms of half-life, which is the amount of time required for half of the atoms of any starting mass of a radioactive isotope to decay into stable product, daughter isotopes. And after one half-life, half of the parent atoms are changed into equal number of daughter atoms. And after the second half-life, half of the remaining radioactive isotope would still exist. So with each successive half-life, the remaining parent isotope is reduced by half. So we can see this in terms of ratios. To begin with, let's say an igneous rock solidifies, it crystallizes. It's got a full 100% parent and it's got no stable daughter, so it's all reactive. Therefore, after one half-life, you're going to have 50% of the radioactive isotope still and 50% of the stable daughter, and the ratio is 1:1. And then as we continue to go sequentially through different new half-lives, as time goes on, it's only the parent that's decaying. But as the parent decays, we're going to be decreasing parent proportionally, and we're going to be increasing the daughter, the stable daughter. And we can look at these ratios to determine exactly what the half-life is based on the ratio of parent to daughter. And notice I switched this to be parent to daughter, so I don't know why I did that. So this should be 1:0. So, okay, moving on. Moving on here. So here we have these radiometric graphs that if I have 100% parent, as it's decaying, I'm gaining the number of stable daughter. And I can see this if I look at this graph. If I start off with 100 parent isotope atoms, after one half-life it's going to be 50% parent, 50% daughter. And then as a second half-life it's going to have 25% parent, 75% daughter. So its ratio is 1:3. So let's say we flipped pennies, because there's a flip pennies activity that sometimes we get to, sometimes we don't. But if we flip 20 pennies and use the head side to represent the radioactive parent, the tail side would be the stable daughter. So after one flip, or one half-life, roughly 50% of the pennies would be heads up and 50% would be tails. And this is analogous to having 50% of the isotope that is unstable and 50% stable. That your ratio of 1:1 tells us that it's gone through one half-life. And we could continue flipping the head side and we would see it roughly be 50%. All right, half of it would decay. And therefore, how do we know how old a rock is? Well, radiometric dating provides this. That once a magma or lava solidifies, its radiometric or the clock, right, the timeline begins. By knowing how to do the scientific process, we can confidently come up with this absolute time. That rates of decay are known as the half-life. So once a geologist determines the number of half-lives, he or she can multiply the time it takes for the sample to decay and find the actual age of the sample. So here are some examples of radioactive parents, the stable daughters, and their half-lives. That when we look at rocks, we can say that, well, silicates contain radioactive minerals. That potassium-40 is found in potassium feldspar and muscovite mica, and uranium is found in zircon and apatite. And if we were to graph the flipping pennies activity, we would get a graph that reflects this very feature, the trends of these graph lines. We see that our parent's going to be decreasing and the daughter is going to be increasing. So there's a couple assumptions. There's 3 rules that are applied to radiometric dating. One, that we never really know the initial conditions, but we assume that the conditions were nothing different or special. We assume, the concept of what took place in the past is the same that's taking place today. So we have these conditions that we don't know, but we assume. We also assume that there's no addition or loss of the parent or daughter, the isotope, when in the decaying process. So we must assume that the total ratio that we have found consists of only the decaying parent and stable daughter isotope. We assume that they were trapped completely in the crystal and in the matrix of the igneous rock that we're radiometrically dating, or within the mineral structures. So we're assuming that nothing's lost and nothing's gained. And lastly, we also assume that the rate of decay is constant. So these 3 rules are assumptions that are made in radiometric dating. And for the most part, they stay true. So we can do these practice problems, and we always have a chance to do them in class. I've got 5 scenarios for you with different, let's just say different radioactive parents and daughters, and we can calculate the times. And here's the answer key. I left it upside down so that you don't look right at the answer. But you can try this. And last but never least, you can read this, and I always recommend you do. But I want to make sure we understand radiocarbon dating. A lot of times we will be using, for deep time, we use potassium 40 to argon 40 decay rate because they have just a much larger half-life. Or we could use uranium to lead. That these are old, very, very large half-lives. But we use radiocarbon dating to measure radioactive isotopes of once living organic material instead of rock. That radiocarbon dating is used on organic materials that are younger than 60,000 years, or relatively young in geologic terms. Geologists use radiocarbon dating of wood, bone, pollen, insects, animals, or anything that was once alive. So radiocarbon dating is a more recent timeline or substance, and we can apply this to the Great Ice Age, whereas deep time we use different isotopes.